Welcome, everyone.
Hello.
Thank you so much for joining. So today we're going to talk about integrated UAV simulation workflows, mainly focusing on combining MathWorks tools and the PX4 architecture. My name is Ronal George. I'm an application engineer that focuses on robotics and autonomous systems. And with me I have...
Hi, everyone. I'm Mihir Acharya, and I'm a product manager in the Robotics and Autonomous Systems group at MathWorks. All right, so I'll take it from here. So we'll talk about a workflow that integrates MathWorks tools with PX4 architecture. So let me start with some background. So simulations have been used for ages in aviation industries, like flight simulators, to train pilots in getting familiarized with complex systems and their responses when they're flying the aircrafts. So even before flying, they would test all those cases within these simulators. Then came the drone simulators that trains drone pilots to fly these drones for various use cases like inspection, photography, and several different applications. But what in the case of an AI pilot? So a UAV also needs simulation similar to a human driver, because we want to train our algorithms for all these various different edge cases that in past humans were being trained for. And there are several different reasons why a drone may crash. And that's what the main point about simulations are. We want to ensure safety, and we want to ensure a drone should not crash. So several different reasons a drone can crash can be controller errors, mechanical rotor failures, varying payloads, and also other conditions like environmental effects, changes in weather, or failure of autonomy algorithms, or sensor failures. If you click. So, and one of these sensor failure application we will go over, and Ronald will go over that. But before that, let me bring over why MATLAB and Simulink and why MathWorks is here with all the PX4 ecosystem that also includes a lot of open source like OpenCV, ROS. So let me ask a quick question here. Anyone of you used MATLAB or Simulink in past? Yay. Great. So maybe we don't need to go in detail what MATLAB is. It's a programming environment to develop algorithms for data analysis, scientific computing. And then if you click, we have Simulink for model-based design, graphical user interface for designing, simulating, testing, verifying, and deploying various different types of applications. And within MATLAB and Simulink, we have 120 add-on products that specialized for different applications. And these are all those different workflows and applications. And if we click one more time, this is what we are going to talk about, mainly robotics and autonomous system tools that relates to the UAV architecture. So how we project MATLAB and Simulink is like an integration platform. So you develop your applications within MATLAB and Simulink using a lot of different pieces that comes together via various different types of integration or interfaces we have built. For example, we have interfaces with ROS, Unreal, OpenCV, and also with PX4 architecture. So we have been working with a lot of customers in various industries, and now we have some really great use cases, success stories for PX4 controller deployment from Simulink. And NASA recently was one of our customers we worked with to deploy a Simulink controller on a quad rotor. And the biggest USP was that they were able to do this, reduce their time significantly at the degree of going from days to minutes in deploying a Simulink controller. And Ronal actually worked them on this, and I would like Ronal to add a few points here as well.
Yeah, so I'm actually going to go over to the next slide and let this kind of play on while I talk about it. This is the first project that we started working with NASA on. This is a quad rotor that they were developing. It's kind of their prototype test platform. This is to validate the entire workflow. So I will take an example and go through how you go into identifying your controller, identifying your plant parameters, tuning your controller, and deploying it overall. But they started with the quad rotor and eventually want to go to custom platforms. The capability that you get here is your control laws can be deployed directly onto PX4 using MATLAB and Simulink. So be it you have a tail sitter, you have a fixed wing with 14 servos, you can build the controllers directly from MATLAB and Simulink and deploy it onto a PixHawk or a PX4 board. Yeah, I'll let Mihir go through and I'll talk about an example later.
Awesome. So to do something like that, there are several different building blocks we have to consider. So for simulation, something that we start with is designing the plant dynamics or plant model and flight controller, for which we provide a lot of baseline models out of the box that someone can start with. And then we also design autonomy algorithms along with that to make your flight autonomous. And next we have visualization capabilities like integration with Unreal for scenario simulation. And how you bring in waypoints to the simulation is through connection with ground control station. So we have several different ways you can connect with ground control station as well. And finally, when you have tested your algorithms in simulation, you would like to deploy it on something like a PixHawk board for hardware in the loop simulation. So a lot of steps before we actually go out and fly the drone to ensure the safe operation. So this is the workflow we're going to talk about today, and Ronal will give some demos, show you some demos on that. But just painting the high-level picture here, we have our inputs from a ground control station, QGC in this case. We have our baseline model for controller designed and tuned in Simulink, and it is in a feedback loop with the plant model, which we provide along with that. And then we have scenario simulation, where we have an asset of the drone flying within a photorealistic environment, which is following the representation of the drone using the plant model. And we also have sensor models that detect various different objects in these photorealistic simulation for the autonomy algorithm to react on that. And finally, the autonomy algorithms is designed within Simulink that can also be deployed. So the deployment workflow looks something like this. We deploy our flight controller onto the PX4 board, and here we replace the native PX4 controller with the Simulink design controller. And then to speed up the simulations to achieve real time, we deploy our plant model on something like a high computing platform like SpeedGoat. And finally, we can deploy our autonomy algorithms on a compute board like NVIDIA Jetson. And this is the way we achieve a full hardware simulation, hardware in the loop simulation. So we'll start with a subset of that, which is designing the plant model and controller. So there are several different levels of fidelities to design a plant model. We can really define really high fidelity plant models using something like Simscape physical modeling, or we can go one level down with defining the vehicle dynamics using something like a 6 degree of freedom. Or we can use really simple baseline models to prototype your algorithms. So a lot of times you might not need to go to the highest level of fidelity just to make your iterations or rapid prototyping fast, and use maybe something like a baseline guidance model to train your or prototype your autonomy algorithms. And we need to have our plant model be an accurate representation of your drone. And for that, there is a process that Ronal will walk you through now.
Right, so when you start building your plant, you have some idea of the dynamics of the plant. Mathematical equations are going to tell you what to expect of the dynamics of the plant. You know, coefficient of torque and thrust that you can kind of estimate. You know the wheelbase, you know the CG point. These are some things that you can get close to. But just being close is not good enough to build a controller. You want something very accurate. If you want a really robust controller that's aggressive or stable at any wind load, you have to get a really good estimation of your plant. Now, this comes into a loop, right? If you looked behind, we had a controller and a plant. Now, the controller that we're working with is based off of a PX4 architecture. That's open. You can see what that controller looks like. So what we did first was build a representative controller model in Simulink. The parameters are already available. MC gives you all the gains that you need. So we can quickly do a controller estimation. Now we come to our plant. So if you look at here, you can see that we have a plant model that was not very close to the ideal one. There is some unmodeled dynamics. We used our PX4 architecture to build our initial controller. And then we can estimate the rest of the parameters. And let me show you that as I go through the slides. Right, so take this for example. This is actually UEFI's IFOS. They lent it to us for us to do some test flights. We also got another company to give us a really nice 3-axis gimbal. Of course, we don't have any position control here because it's locked in place. It's not going anywhere. But attitude, you can test out. So first thing we did, we flew the drone. We did all kind of pitch and roll maneuvers and got a bunch of log data. The next step was putting this through our Simulink model. So there's 3 pieces here. You can see there's one that just reads from the log data, one that says controller, and one that says plant. First step, keep it in open loop. Read from log data, send that data to your controller, validate that the simulated controller, as in your actuator controls, comes the same as your log data. Once you have that, and your parameters can come directly from the log file too. If you've seen PX4 logs, you get all your parameters. So validate the controller, make sure it's the same. Next, we can go into closed loop, and we can start looking at what our simulated plant response looks like. So I'm just looking at the state of the plant. If I look at the state of my simulated plant versus my log, I can see clear differences. And this is where the power of simulation comes into play, because now I can do a sweep analysis. I can go and say, okay, you know what? I think my CG is a little off. Maybe my coefficient of drag is a little off. I've set it as 0.002. It might be 10% higher or 10% lower. I'm not really sure. I'll put that as an experiment. I can have experiments with multiple different parameters using the outputs that the simulation makes and the log data. And then I just let it run. It can run for maybe 10 minutes. It can run for 40 minutes. It might get stuck at a local minima, so we'll do a randomized restart. But eventually, I'm going to get a good set of parameters that validates what my log showed to my simulation. So my simulation matches exactly what my log is, which means regardless of the fidelity in which you built your plant, it may be a CAD model, maybe mathematical equations, you know that that simulated model is exactly like your actual plant. This is where now you get to try out cool controller laws. Now you can try, okay, I don't want just a standard acro controller. You can go over to the next slide. You don't want just a standard acro controller. You want maybe a tuned stabilized controller. But we don't want you to go directly and take that controller that you built and put it onto your hardware. We want to take this through stages. These are the 3 stages that we define. First, model. So your controller is in the simulation model. Second, we have software in the loop. So we use POSIX. We built it. We make sure that the generated C code from our controller works as expected. It matches our actual simulated model. And then finally, before flying, we can do hardware in the loop. So actuators are disabled, sensors are disabled, but at least I know once I put this directly onto my PX4 or any board that runs PX4, it's going to give me the same performance. Right. And then I want to show you an example of what we actually built with this. Click once more and it should start playing. So we started with their stock controller that came, and then we pushed 2 different controllers on this. One, an acrobatic, fairly detuned acrobatic for someone who's not very good at flying, so we don't want to lose that asset. And then a much more aggressive stabilized controller if you want to have some fun. Yeah, so a lot of power that you come through when you have a good representation of your plant and you have the power of Simulink and MATLAB to build really advanced controllers. Right, so next, Mihir is going to talk about the second problems, or the second category of problems. We talked about controllers or mechanical or payload in terms of controller and plant. Now let's go to the other scenarios.
Thanks, Ronal. So now we have our plant model and controller designed. Now we want to take this and actually see how the drone is behaving within some realistic worlds. And by that, I mean photorealistic virtual environments. Next. So to build a photorealistic virtual environment, really we have 3 simple building blocks here. We need a virtual asset, which is like a flight drone asset. We need 3D scenes, like the city scene. And we need sensor models that are equipped on this drone to detect the environment data. And we can get all these from Simulink pre-built and integrate it with Unreal Engine to visualize a scene something like this. Now let us take what Ronal just explained and bring it in a scenario simulation. So in the next slide, we can see an example with package delivery drone, where we have the Simulink model that describes ground control station, environment and sensor models, the obstacle avoidance algorithm, and the flight controls and plant model. So if we talk about the environment and sensor model, we have several different blocks that let you visualize this, including your different sensors like GPS, IMU. So you can start with something like a cuboid world, and you can build a simple cuboid-based scenario to start prototyping your obstacle avoidance algorithms. And you have sensor models that uses LiDAR data to detect these cuboids, and you can go from there and extend your simulation to a more photorealistic environment like something shown here. You can also add weather effects or environment effects like rain in this scenario to add noise in your sensor data. And then once you have tested in a photorealistic mocked city scene, you can actually take it to a real world city scene or real geographic location. And for that, you can use something like Cesium platform that we integrate directly through Simulink as well. And then you can also bring in different types of assets like a helicopter or even a vertical takeoff landing hybrid model. And this is a demo that we have where we show a quadrotor flying through the city of Chicago. And you can provide waypoints from QGC to go from one location to another. And while you're visualizing this, you also have accurate representation of your drone via the plant model.
Yeah, just to add something here. So Cesium gives us terrain data. So regardless of where you are in the world with lat long, you get terrain information. And then Cesium also supports OpenStreetMaps, which gives you building information. So instead of building out a simulation environment that doesn't match your real world, use Cesium. You want to fly in New York and see how delivery packages will work? Fly in New York and see how delivery will work.
Awesome. So now we have our plant model, our scenario simulation set up, and we want to test our autonomy algorithms next. So we saw a demo of obstacle avoidance. There are other algorithms like motion planning that you might also find helpful. And we have several different types of path planning algorithms like A-star or RRT that you can use directly out of the box for something like this. Next, we would like to see how we can deploy these algorithms on a compute board, something like Jetson. And we have a couple of demos here that Ronal will showcase next.
All right, I'm going to stay with this slide for a second. So we talked about the controller. We talked about the plant. Mihir gave us an overview on scenario simulation. Now we're going to try build out our autonomy algorithms. Once you have a really nice scenario with so we support Unreal, we support through ROS, you can also work with other simulators. We have an internal simulator that you can use. For Unreal, we actually provide our own sensor models. So LiDAR, radar, camera, depth camera. Now you have sensor data from a really nice photorealistic scene. That's where you can start building out your autonomous algorithms. Now, we don't want you to just simulate these algorithms. We want you to actually deploy them to the target hardware, make sure they work as they will, they don't run out of CPU or they don't overflow memory. So let me show you an example of one of these. You can go over to the next slide. Yeah, and click it once more so it does start. Right, so here you'll see I have QGC on the right. I've defined a mission, just a straight one-point mission. The reason I chose that is because I'm using an existing scene. This is a suburban scene that we provide with the tool itself that you can use. I chose this waypoint because it goes directly through a tree. Now, if I were to ignore onboard communications, on the top, you'll see the drone just goes directly through the tree. It doesn't care. It doesn't know a tree's there. On this, there's slight small windows where you can see an RGB frame and a depth frame. So what we do on the bottom where it says avoid obstacles is we take that depth frame, we convert it to a point cloud, we provide a 3D point cloud obstacle avoidance algorithm, which is based off of vector fill histogram. So it identifies where obstacles are, what positions these obstacles are. If the obstacle comes closer than what I defined as my look-ahead point, it's going to ignore the waypoints that came through telemetry, and it's going to start going around the obstacles instead. So OBC is going to give me modified waypoints. Actually, if you skip through the video a little, there's a, oh, I think it restarted, but that's fine. I just wanted to show you an example of when we go and push our look ahead point much further. Yeah, I think that's good. It's okay. It's okay if it doesn't skip through. But I had a closer view so you could actually see how the obstacle avoidance algorithm works, but you can move over. Right, so coming back to this, the only caveat here, we've deployed our flight controller onto a PX4 based board. We've deployed our autonomous algorithm onto a compute platform that's, has the capability to do your autonomous algorithm. Now your chokehold is your actual desktop that's running the plant. You notice we're still running hardware in the loop, so I don't have any actuators, I don't have any sensors on the PX4 itself. Everything's being simulated in that plant model. So my GPS, my baro, my airspeed sensor, all that is in my simulated model. That becomes a really large model. So that's kind of where we see our chokehold, and we don't want that, right? PX4 needs control commands every 10 milliseconds. It needs OBC commands every half a second, so we have to maintain that rate. This is where we start deploying our plant, which has our sensors, into a real-time target. So no OS in the background, nothing else blocking, no Teams messages coming through. It's just your plant and sensors running. It gives you a lot of interfaces, so if you want to actually connect these to actuators, you want motor spinning, you want battery power to be estimated, all that comes with this target device. It's a proprietary target that we work with, SpeedGoat. If you're interested, I'll be happy to tell you more about it. But yeah, let's move on further. What does that enable now? So if you look at this diagram from, I have serial communications to the flight controller. I have telem data going to my real-time hardware. The first thing I want to do is deploy my actual controller. So that's my controller module. It has a navigation block in there in which it's going to avoid obstacles. That gets deployed, so it's fairly straightforward. I hit the build button. I have to make sure that I have serial communications with my PX4 board here. We use the PXOC4. We're going to update this for the 6X, which we just acquired. This is the device, this is the plant model that gets deployed to this real-time target. You'll notice that there's a couple buttons there called fault injection. And this is why we want to deploy this, because we want to test out what happens if my baro freaks out. I don't know if you guys have had that happen before. The first time I flew my drone, my baro freaked out and my flew just took off, flew up, and that didn't land really well. What happens if you lose GPS satellites? You want to test these out? With this, we can actually start injecting some of these failures directly to your plant. So here's a simple flight that I was doing where everything works as expected. You'll notice a difference. Once I've deployed this plant model, things start running a lot smoother. My visualization's the only thing on my host computer, so no bottlenecks here. Right, so this is a simple straight mission. 3 waypoints, go there, come back and land. You can see on the top in QGC, I have great number of satellites, so GPS is valid, nothing's wrong. And I've completed my mission. So I've done a basic test. But now if I wanted to go and see what happens if I say, I don't know, I have a lot of mag interference because I had some really thick cable sitting around my PX4 and I didn't realize it. But I can start inducing that. Here what I do is I go ahead and enable GPS loss. So taking off, remove the number of satellites. What is my drone going to do once it doesn't have it? These are the kind of tests that you can do once you have these running on hardware. You can validate if your drone's actually going to perform the way you wanted it to. Is it going to use maybe visual inertial odometry to move it along? What's your redundant failure modes if something fails? Go ahead. One more clip. So I hope that covered the larger model that we wanted to talk about. There's 4 steps that we went over today. One was first build an accurate plant representation, because if your plant's not accurate, what controller are you actually building? The second is use our tools to build more advanced controllers. We actually just put a new a controller onto the PXOC. It's a model reference adaptive controller. We're testing it right now. Our goal is to be able to remove one of the propellers and still land safely. The last, of course, we talked about scenario simulation. You can test out everything in low fidelity if you want. You can go to much higher photorealistic scenes. You want to fly in a city with buildings and actual terrain, we support that. And then finally, we don't just simulate, we deploy to target devices so you can validate that these work on your target devices before you go actually fly it. Don't lose your assets, guys. Test and then fly. All right, to close off, I know I didn't talk about the 3 different modes, which is model, simulate, deploy. We have a video that we did on it, so if you're curious, make sure to look at that. All the content that we presented should be available if you scan that QR code. So slides are available, some resources, how to reach us. But the floor is open now. So any questions on what we talked about? Thank you.
Thank you.
I know that was a lot of content. Yes, please. Rishikesh, right?
My question is, have you tried simulating weather?
Yeah, so if you go back a couple slides, in Unreal, you get access to some weather. You can say where the sun is. So is it northward? Is there a lot of shadow? You can add rainfall. We've tested that with our point cloud sensor. So you can actually see reflections coming from your LiDAR rays. So that kind of weather effects you can do. It really depends on how much the simulator supports your photorealistic scene. Now, there's a benefit to this. At the end, you're getting an image frame or a point cloud frame. You can inject noise into that. You can add a cluster of birds into your point cloud and see what that is. It's just a couple points in space. So because you bring this into MATLAB and Simulink, you have all the pre-processing power that you need. Yeah.
How much is the speed code?
They range based on the amount of UI that you want. So if you want a large one, I think they range between 5 and 25,000, based on how many peripherals do you want to actually connect? How many CAN ports do you want? Oh, talking about that, UAV CAN is being supported now. It'll be available starting our pre-release, which is like a month or 2 from now, if you're interested.
Cool. Any
Anything
other
else?
questions?
Yeah, please. I'll come right to you.
Since you move some forensic communication initiative,
Uh-huh.
so what's happening when your drone moves from the ground station? If you lose the communication.
Right, so when I'm flying here, so far it's just been telemetry, right? I'm getting RF data. But if you're going to fly further out, you have to consider something like a software-defined radio or a mesh network that's going to give you communications. If you lose communication, what do? What's your next step? What are your redundant ways of actually coming back to your return to launch? That's what you can test here. You disable comms. Maybe you have a fix on where you are with your current GPS, and then try to return. These are things that you can test out as you build out these simulations. Yeah, and we do actually give you, within MATLAB and Simulink, you can define your beamforming, your antenna patterns to decide, what kind of range and what kind of bandwidth do I get at certain distances. So things that you can simulate and test. Yeah, sorry, go ahead.
You said the Unreal Engine you can test against visual things like rain, sun, and such.
Yeah. So wind's actually I don't need Unreal to test wind. I can just change the attitude of my drone, induce an attitude shift, and say that's wind. I can be calculated based on like if it's a fixed wing, I expect, if I get a lot of wind coming from here, it's going to do a side slip. So we have wind effects as a part of our low fidelity model, which means I can say what's my northeast down wind currently. But wind's actually something that I just do a attitude induction to see. So in the NASA story that I was talking about, that's one thing that they do right now. They do input perturbations to see, actually to identify their plan. So they say, we're flying great with a certain headwind. Let's do a step response of, what if I stall and I'm falling to the right? Can I control that? How is my platform going to react to that stall? So they test that in an actual test bench, and then that tells them what their actual plant model looks like. So they can control that in simulation and then test it. Yeah? Yeah, please.
So I have a working simulation in Gazebo with multiple drones carrying a slum.
Okay.
How difficult is it for me to take that SDF file and simulate it in MATLAB so I can do some more controls up and stuff?
Really good question. So we do import SDF. I hope the SDF is not defined with all your assets in it too. I would remove the drone assets and then bring them as an SDL or a separate SDF, so they're different assets. You don't even have to bring them in. We can communicate with Gazebo. So if you have ROS running in Gazebo, MATLAB speaks ROS. Tell me what your published topics are, or subscription topics are, and we'll just talk to them. So you can actuate it by ROS. You can read sensor data with ROS. If you want to bring that scenario into MATLAB, we import the SDF so we can recreate kind of a low fidelity scene. So a lot of ways. Yeah? Please. Do you want to take one?
I think we're out of time. We have another session after this. Yeah. But
I'll just connect with you after this.
yeah,
I was just going to say for delivery, your weight would change.
As you drop it.
So you can inject that into the platform.
Sure, yeah. You can, I guess that's one thing now, right? If I was going to deliver there's CG changes as I'm dropping it as it goes down. Once I leave it, my CG changes, so I have to control it through that. These are things that you can simulate and test out. Awesome, thank you so much, Sharon. Thank you so much for the questions.